Hi guys, welcome to MedEd Next. This is Dr. Patil, your faculty for medicine. And in this video module, we have already done the basics of ABG in the previous YouTube live session. So in this live session, we will continue from there. Okay. So what we are going to do today is we will take up one ABG as an example, right? We have already done few examples. So we will take up one more example today. And this will be an ABG which will require some additional steps other than what we have covered in the previous module. So let me first start by projecting the ABG problem. So here is the problem. Patient's ABG, pH is 7.23, partial pressure of oxygen is 70 millimeters of mercury. The carbon dioxide partial pressure is 17 millimeters of mercury, and bicarbonate is 7 millimoles per liter. Chloride is 97, and they have also told us about the patient's sodium, which is 123 millimoles per liter, and then they're asking us to analyze the ABG. Okay, so what do you think? What is the ABG abnormality here? Is it acidosis or alkalosis? That is the first step, right? And if you know whether it is acidosis or alkalosis, then the next step is to identify whether it is a respiratory pathology or whether it is the metabolic abnormality, right? Okay, so let us do that. First step is to assess whether there is acidosis or alkalosis. So here the pH is 7.23. The pH is 7.23. Okay, now when the pH is less than 7.35, we call it as acidosis, and when it is more than 7.45, we will call it as alkalosis. 7.35 to 45 is the normal range. So here what do we have? We have acidosis or alkalosis? Obviously we have acidosis, right? So this ABG shows acidosis. Now once we have acidosis, we need to now ascertain whether it is a respiratory acidosis or metabolic acidosis. So how to distinguish whether it is respiratory acidosis or metabolic acidosis? I have given you a mnemonic, right? In the previous YouTube live, I have given you a mnemonic called as MS Ortho, right? Do you remember the mnemonic? MS Ortho, or if you're already familiar with other ways of remembering it, even good, right? ROMS or ROM. Now MS Ortho, this mnemonic can be applied by looking at two parameters. One is partial pressure of carbon dioxide and other one is pH, right? pH and partial pressure of carbon dioxide. So we have to just plot whether the pH and PaCO2 are decreasing or increasing. So in this case, the pH is decreased, less than normal range. Normal range is 7.35 to 7.45. So in this patient, pH is decreased. Okay, what is happening to PaCO2? The PaCO2 normal range, let me bring that data. PaCO2 is 17 millimeters of mercury. Normal range is 35 to 45, right? So when we talk about PaCO2, normal PaCO2 range is 35 to 45 millimeters of mercury. Okay, how much is it here? It was 17. So it is decreased or increased? It is decreased. Decreased. So pH and PaCO2 are following the same direction. Both are decreased. So the mnemonic applies like this, right? If both are in the same direction, metabolic, it is same side. MS Ortho stands for metabolic, same side, right? Ortho ka R stands for respiratory. Opposite, respiratory. So here both are in the same direction. So whatever pathology we have is a metabolic abnormality, right? So we have a metabolic abnormality. So now what is the conclusion on this ABG? We have metabolic acidosis, right? So this ABG is showing metabolic acidosis. Showing metabolic acidosis. Okay, now that is done. We know we are dealing with a case of metabolic acidosis. Now we should also calculate the appropriateness of compensation, because whether the ABG changes that we are seeing here. Okay, see, normally what happens in metabolic acidosis, the bicarb will be decreased, right? Now to compensate for decreased bicarbonate, even the carbon dioxide will be washed out and you will have a decrease in PaCO2. So the primary abnormality is decreased bicarb, and the compensatory mechanism from the respiratory side is the decrease in the PaCO2. Okay, but what if there is another additional ABG abnormality, right? So you never know whether it is just the compensatory change in the PaCO2 or patient also has an additional respiratory acidosis or alkalosis, right? To understand that, we need to see whether this compensation, the PaCO2 is as per expectation depending on the patient's bicarb levels, or it is more or less. That will help us to unearth an underlying additional ABG abnormality. Okay. So in case of metabolic acidosis, how to calculate appropriateness of compensation, right? In case of metabolic acidosis, how to calculate the expected compensation. I've already told you the abnormality here is decrease in bicarb. Abnormality is decreased bicarbonate. Okay. And compensation will be in the form of decrease in PaCO2. Okay. Whether PaCO2 has decreased appropriately or not, that is what we need to know. So we can calculate the expected PaCO2. For that, there is a formula which is called as Winter's formula. Let us calculate the expected partial pressure of carbon dioxide in a case of metabolic acidosis. The formula that we use is called as Winter's formula. Winter's formula. Okay. Now, what is the formula? The formula goes like this. For calculation of the appropriateness of PaCO2, we need to have the value of bicarbonate. Okay. So, formula goes like this. Expected PaCO2. Expected PaCO2 is equal to 1.5 into patient's bicarb levels. Okay. 1.5 into bicarb levels, plus we will add an 8 plus or minus 2 to get a range. Okay, so let us apply this here. Now here the patient's bicarb is how much? It was 7 if I remember correctly. The bicarb was 7, right? The bicarb was 7. So let us take that to the formula. 1.5 into 7 plus 8 plus or minus 2. That will give me the expected PaCO2, right? 1.5 into 7 will be 10.5 if I have not mistaken, right? Yeah, that will be 10.5, okay, plus 8 plus or minus 2 to get the range, okay. So 10.5 plus 8 is 18.5 plus or minus 2. So we will have a range of 18.5 minus 2 will be 16.5. 16.5 and 18.5 plus 2 will be 20.5. So this is the expected PaCO2, right? Expected PaCO2 range is 16 to 20, 16 and a half to 20 and a half. Okay, how much is it in this case? In this case, PaCO2 is 17. So is it in the expected range? Yes, it is in the expected range. So that means this patient has appropriate compensation from the respiratory system, not more, not less, no additional ABG abnormality here, right? So that is our second take-home message. So we have metabolic acidosis with appropriate compensation from the respiratory system. Okay. Now, having understood this much, the next thing we go on this ABG is to calculate what is called as anion gap. Now, you might ask me, sir, we know it is metabolic acidosis. We know there is appropriate compensation. Then why do you want to calculate something called as anion gap? Now, see, once you have a patient with metabolic acidosis, I have to take it to the diagnosis of cause for this metabolic acidosis, and that is where this anion gap comes into picture. Okay. Now, what is anion gap? Anion gap is nothing but the difference between measurable cations and anions. So normally what are the cations that we measure? We measure sodium and potassium. Those are the routinely measured cation. Other than that, if you ask me, yes, we have magnesium, we have calcium, right? Plenty of cations. Then what are the usually measured anions? Your chloride and bicarbonate, right? Apart from that, you have phosphate, sulfates, right? Those are all anions, but they are not usually measured. So this anion gap is basically telling you the difference between the measurable anions and cations, and this gap accounts for those anions which are not included in this measurement, right? But remember, human body will always have a balance of equal number of cations and equal number of anions. There is balance, but because the measurable anions represent a group and measurable cations represent a group, but there are unmeasurable cations and anions, we get this difference. Okay. Now, the formula for anion gap calculation, either takes into account sodium plus potassium for the cation side and the bicarbon chloride for the anion side, or sometimes only sodium. Both are fine. If they have given the potassium value, you can use it. If you are not given, then you can only use sodium. Okay. So if you're taking into account the anion gap only looking at the sodium, then the normal anion gap is around 12. Okay. When it is less than 8, we will call it as low anion gap. And when it is more than 12, we will call it as high anion gap. Right. So most importantly, we have to differentiate whether there is high anion gap or not. If there is a high anion gap, then there are set of causes for it. We call it as 𝐒𝐿𝐼 or high anion gap metabolic acidosis. Similarly, we have a condition called as �NEGMA, right? That means non-anion gap metabolic acidosis or normal anion gap metabolic acidosis. Now you might ask me, sir, what if the potassium value is also given? Okay, then add 4 to it, because normally potassium ranges between 3.5 to 5.5. You can take a median value of 4. So if potassium is taken into account, if potassium is included in the formula, okay, in that case, your normal anion gap becomes approximately 16. Okay, so in that case, the normal anion gap becomes approximately 16. We are adding 4 for the potassium. Okay, now how this is going to help? Mainly to identify the cause for acidosis. Okay, so let us apply that for this patient. Let us calculate the anion gap for this patient. Okay, I'll add a page here. Anion gap on this ABG. We know the sodium value, right? We know the sodium value, we know the bicarb value, and we know the chloride value. Okay, so let us calculate. Sodium, if I remember correctly, was 123 millimoles per liter, minus bicarb was 97, and the chloride was 97 and bicarb was 7. Let me recheck one more time before I put it into calculation. Yeah, so bicarb was 7 and chloride was 97, sodium 123, right? Okay. Bicarb, sorry, again I exchange it here. Bicarb is 7 and chloride is 97. Okay. Now let us calculate the anion gap. 123 minus 97 plus 7 is 104 if I am mathematically correct. So that gives me a value of 123 minus 104. Okay. That gives me a value of 19. Am I correct? No, not 19. Okay, how much is it going to be? My mathematics is really weak, guys. I am not a maths buff at all. Let me calculate. 13 minus 4 is 9. 2, 1. 2 minus 1 is 1. 1 or 1 minus 1 is 0. Yeah, so it is 19. The anion gap here is 19. Okay, anion gap is 19. So we have high anion gap or normal anion gap. The normal anion gap is approximately 12, right? So you can say 8 to 12 as a range. When it is less than 8, you have low anion gap metabolic acidosis or 𝐒𝐿𝐼, and when it is more than 12, you have high anion gap metabolic acidosis or 𝐒𝐿𝐼. So this is a typical case of high anion gap metabolic acidosis, right? So what we are dealing in this ABG is a high anion gap metabolic acidosis. Okay, does the story end here? See, we have identified whether this is acidosis or alkalosis. We know whether it is respiratory or metabolic, right? We know whether the compensation is appropriate or inappropriate. That way we know whether there is a single ABG abnormality or there is an additional acid-base disorder. Then we have also calculated the anion gap, and we know that what we are dealing here is a high anion gap metabolic acidosis. Now in patients who have high anion gap metabolic acidosis, what if they have an additional non-anion gap metabolic acidosis also intervened into it? Possible, right? Patient may have two metabolic acidosis, one high anion gap, another normal anion gap metabolic acidosis. So how to distinguish between these two? For that we have to calculate one more thing called as delta gap. Delta gap, right? What is delta gap? Delta gap is given with this formula. How to calculate? What is the patient's actual anion gap minus 12 as a representation of normal plus patient's bicarbonate levels. This gives us the delta gap. When the delta gap is more than 18, you have a single ABG abnormality. That means, okay, you had made a diagnosis of high anion gap metabolic acidosis. Remember, we come to delta gap only when, right? Only if there is a high anion gap metabolic acidosis to understand if there is an additional non-anion gap metabolic acidosis. Okay. So if this delta gap is more than 18, that means you have a single abnormality. So it is only a HAGMA, nothing more than that. But if it is less than 18, you have an additional non-anion or normal anion gap metabolic acidosis in addition to high anion gap metabolic acidosis. So let us do this. With this, we will conclude this ABG question that we were talking about. So in this case, what is the actual anion gap, right? In this ABG that we are talking about, let us apply this formula. The actual anion gap of the patient was 19, if I remember correctly. Correct me if I'm wrong. Minus 12, right? Plus bicarbonate was 7. So that gives us the delta gap, right? Delta gap of this patient would be 19 minus 12 will be 7 plus 7. So delta gap turns out to be 14. Delta gap here is 14. So if delta gap is 14, what does it indicate? Here we have a additional non-anion gap metabolic acidosis. So what is the conclusion for this ABG? Let us put everything in one place. Okay. So what we are dealing here, right? The final diagnosis, let us nail it. What we have? Number one, we have acidosis because the pH was 7.23. What type acidosis we have? We have metabolic acidosis, right? We have metabolic acidosis because PCO2 and pH both were decreased. They were following the same direction. So we have metabolic acidosis. We have calculated the anion gap. So this metabolic acidosis had a high anion gap. Anion gap was 18. So it is a high anion gap metabolic acidosis. And because it was a high anion gap metabolic acidosis, we also calculated the delta gap, right? And how much was the delta gap? Delta gap was 14, less than 18. That means there is an additional non-anion gap metabolic acidosis. So we have a high anion gap metabolic acidosis plus non-anion gap metabolic acidosis, both in the single ABG, right? So this is how we get to the precise diagnosis of the ABG abnormality, right? So follow the steps that will take you certainly to the last conclusive diagnosis. Now this question can have options, right? They can give this ABG and ask you whether this patient has metabolic acidosis with respiratory alkalosis. One option, right? Here there is no respiratory alkalosis as a pathology. There is an appropriate compensation. Second option can be it is just high anion gap metabolic acidosis. Third option, there is a high anion gap metabolic acidosis plus a normal anion gap metabolic acidosis. Fourth option, this is a non-anion gap metabolic acidosis. All of these are potential options, but it is pretty easy if you follow the steps, right? So let me recap one last time before I conclude the session. So we had this problem of a patient with this ABG picture. pH was 7.23. It is less than 7.35. So that is why we called it as acidosis. Okay. And because bicarb is decreased and PaCO2 is decreased, PaCO2 and pH in same direction, we called it as metabolic acidosis. Okay. Once we have a metabolic acidosis, we calculated the appropriate compensation by using the Winter's formula. And Winter's formula told us that the PaCO2 is within the expected range, right? So we have metabolic acidosis with appropriate respiratory compensation. So there is no additional respiratory abnormality. Appropriate respiratory compensation is what we had, right? Okay. Then because this is metabolic acidosis, we calculated the anion gap. Anion gap turned out to be 19, which is on the higher side. So we called it as high anion gap metabolic acidosis. Okay. And once we have a high anion gap metabolic acidosis, to see if it is a combination of high anion gap and normal anion gap metabolic acidosis or just pure high anion gap metabolic acidosis, we calculated the delta gap, right? Here it is high because the anion gap in this case was 19, right? Anion gap was 19, which is high. Okay. And we called it as Like we calculated the delta gap to see if it is just a high anion gap metabolic acidosis or whether we have a additional normal anion gap metabolic acidosis. Delta gap was 14 here, that is less than 18. That means there is an additional non-anion gap metabolic acidosis is also there, right? That is how we reach the final conclusion of this ABG. Okay, so in your next exams, you can get ABG problems where you need to finally boil down to this precise level of diagnosis. But at the context of the NEET PG or FMGE, I do not expect them to take you through 3 or 4 minutes of calculations and then come out with the diagnosis. So mostly it will be at a very peripheral level, asking you to identify whether it is the acidosis, alkalosis, respiratory, metabolic. They may go one step ahead and ask you to calculate the appropriate level of compensation, right? In the previous video module, I have shared you the table where the appropriate compensation for all the ABG abnormalities has been mentioned. So I would expect you to literally memorize them. If you know those compensatory formulas, then you will be able to deal with most of the questions coming from ABG. Now, for those students who want to nail it, like any question coming from ABG, you want to nail it, we should come to this point, right? So on this session, that's it from me, guys. We will connect further again in the subsequent YouTube live sessions. Let us take up these clinically oriented problem solving kind of questions, right? If you have any doubts, you are more than free to communicate with me on the MedEd Telegram group as well as the Facebook group. Thank you.